Welcome, everybody. Nothing much has changed since yesterday. Still in here. Did you have time to look at the things we discussed yesterday? Roche experiment, special relativity.
I have actually a question about this experiment.
Yeah.
Maybe very stupid, but still like.
No stupid
forces.
Questions. Yeah.
We have gravity force. We have tension from the rod. And
yeah.
We have the inertia force, the centrifugal force.
Yeah.
But I don't understand why the torque might appear, because gravitational force and centrifugal force, they're in one plane, right?
Yeah.
So why there is another force that makes the system rotate?
It's well, because it depends. It has to be that the two balls are made of different materials.
So they have different masses.
It's the goal of the test is to test the fact that the ratio of inertial mass is equal to the gravitational mass, right? If it's different for different materials, right? If this ratio is different for different materials, right, then the ratio of these forces F2 over G2 would be different than F1 over G1. Now, these have components. This F2 have components in the x-axis, right, and in the z-axis, according to the way I plotted it. But they will have to cancel out, right? The y, but the x1 would not cancel out. Think a little bit more. Give you a problem set on that. So you can, I told you, this subject is full of tricky things. So, but this is a simple thing. Just think of that and you'll say it right away. Okay. So today, we're going to really begin. So we begin the discussion by special relativity. Again, I want to urge you, we're going now for a week of a holiday. Please do yourself a big favor and review the material you already know about special relativity, so that it will be fresh in your mind. Okay? Because what we're going to do now, we're going to do special relativity, but it's going to be done in a very different way than the way that you are used to. Okay? But the physics is the same physics. Physics has not changed. Okay? Again, as I told you, I mean, I'm sure you've seen special relativity. If you haven't, I taught that once to first-year students. So you can go online, you can find my own old website, go to lectures and first year, and you can find it there. But it's no better than any other source that you have. Okay, so we begin by the principle of special relativity, which is a consequence of the Michelson and Morley experiment. Right? And the principle states that the laws of nature are invariant in any inertial reference frame. Right, let's write it down. The principle of special relativity the laws of nature are invariant in all inertial reference frame. And of course, the experimental basis for that is the Michelson and Morley experiment, which showed that the speed of light is constant for two observers, which may be moving with respect to each other at constant speed. This, of course, contradicts experimental basis. Michelson and Morley. That contradicts Galilean transformation. Right? So, if we have an object, right, so this is my reference frame, and I'm seeing an object which moves at some velocity v, and you are moving with respect to me. Just want to make sure that at some velocity u. So I see you moving at some velocity u. Right. Then Galileo said that you would see the moving object moving at velocity v prime, just v plus minus u. Right. So this is ruled out. Instead, we have the Lorentz transformation. Right? Just before that, right? So let's consider that we have two observers, right? One is reference frame O, we'll call it, and a second has a frame O prime. Now, as you know, in special relativity and in general relativity, you have to be very, very specific and very, very careful in how you define things. Right? So let's say we have a second observer, the purple person, and he has a frame O prime. Right? The black person has a frame O. Now, the coordinates of the black person, right? We'll write down the coordinates at x, y, z, and t. Right? So this black person will specify an event, and I'm stressing the word event because in special relativity, the easiest by far way of thinking is in terms of events, single events that happen. Each event is being specified by its space, x, y, z, and time. And of course, the purple observer, which may be moving with respect to the black one, specifies the same event in his or her frame using his or her using the coordinates, right? X prime, y prime, z prime, and t prime. Right? So both refer to the same event. Right? Something happens. Right? Really, I'm stressing it's going to save you a lot of trouble once you get used to think in terms of events, right? Somebody scored a goal. That's an event that happened at a certain location at a certain time. Okay? Two people kiss. It's an event, right? A photon was emitted. A photon was observed. These are two separate events. Okay? Each event is characterized by space and time. But each observer has its own reference frame, own location, and own time. Okay? Now, let's assume, right, without loss of generality, this observer O prime is moving with respect to the observer O, right? Well, let's assume, again, without loss of generality, that at time t equal t prime equal to 0, their origin of coordinates coincide. Okay, so at t equal t prime equal to 0, the origin of coordinates coincide, right? It's just without loss of generality. The coordinate origin coincide. It's without generality. Now let's say that we have a light source, such as a lamp, right? That at time t equal to 0 and space 0 emits a photon. Okay. Of course, since they're coincide at t equal to 0, then this will be the same in that frame. Right? So if we look at some time t later, right? The wavefront of the light will be where? Right? At what location? At time t later, the first observer O, right, will see the front of the light wave at location. Now, what is the location? Spatial location. At location x squared plus y squared plus z squared equals c squared t squared. Right? The light trouble will arrive. Okay? What would the observer at O prime say? Where is the wavefront of the light is seen by the point of view of the observer O prime?
Same, just with
exactly the same, right? So x prime squared plus y prime squared plus z prime squared equals c squared t prime squared. Now again, let's assume without loss of generality that O prime moves with respect to O only in the x direction. Just our choice, anyway. So in that case, we have that y is equal to y prime and z is equal to z prime, but x is not equal to x prime, right? So assume again that O prime moves with respect to O only in the x direction. So in that case, we have y is equal to y prime, z is equal to z prime, but x is not equal to x prime. So from these two equations, we get immediately the what? What can you say when we look at these two equations? That t is not equal to t prime, exactly, right? So t must be different than t prime. Which kind of makes sense, right? Because if the speed is the same and x is not the same, well, then the time cannot be the same. So that means that time separation is not the same in both frames. Right? Remember, we think of two. What we really did here was a simple experiment. Think of two events. The first event was that a photon was emitted, And the second event was that the photon was absorbed, right, or detected. Right? And we saw that they disagree on the time. In technical terms, right, or physical terms, we say that the time is not an invariant quantity. Invariant means it's the same for different observers, right? But can you think of a quantity which is invariant?
Besides C?
Sorry?
Besides the speed of light?
Yeah, the speed of light is a constant of nature. I'm looking at a quantity that both observers, although they're sitting in different reference frames, would agree that is the same for both.
The difference between lengths?
Exactly,
Square.
exactly. So this quantity is called the interval. We call it interval. And the definition is the interval squared, denoted by delta S squared. I define it to be exactly what's written here. Minus C delta T squared plus delta R squared, which is just minus C squared delta T squared plus delta X squared plus delta Y squared plus delta Z squared. So the interval, right, is an invariant quantity between two events. Right? That's why we have the delta t, delta x, delta y, delta z. You know, this is the difference between two events. So here, again, we had two separate events. Event number one, the photon was emitted. Event number two, the photon was detected, right? The physics is independent on the coordinates. It's independent on the observer. Photon was emitted and the photon was detected regardless of who was looking at it and from what frame. But each one describes these two events in a different way. They would disagree when they go and compare their notes. They would disagree on the x location of these events and the time that it took. But both of them would agree on the interval between these two events. Yes? Delta t squared.
So you take the difference and square?
Well, this is just defined as the interval squared. It doesn't matter because it's the same. So if you take a square root of that, it will still be the same. I mean, I just defined it delta s squared, right? I could have called it delta s. You know, I just moved it to the here, and I get a 0.
But I mean, it's not T1 minus T2.
No, it is T1 minus T2 squared.
Because from that, it looks like T1 squared minus T2 squared is the invariant.
No. I remember. This is really when the light wave was detected, right? When was it emitted? X equal Y equals Z equals 0 and T equals 0, right? So it's delta X is X minus X0, so X minus 0, Y minus 0, right? Don't get confused. In fact, there is a very simple analogy, which makes things easy to understand what is the meaning of the interval. And the analogy is a distance in Euclidean space. So if I look at the concept of a distance in Euclidean space, this is also something which is invariant. Let me show you what I mean. So this is an analogy. Analogy to the interval, distance in Euclidean space. So let's look at simple Euclidean space, two-dimensional Euclidean space. Right? So let's say I have a point here, right? Right. The coordinates of the point is x1 and y1. Right? Now I have a second point. Put it here, it's x2 and y2. Right? Now, if I now look, I have a second observer. Right? Maybe I should be a bit more precise in the way I plot it. This would be like x1, this would be like x2, this would be y2, and this is y1. Right? Now I have a second observer whose frame is, let's say, rotated with respect to the first one. Right, so this is the frame O, and this is the frame O prime. So in the frame O prime, right, the location of the same points, right, would be x2 prime and y2 prime, and x1 prime and y1 prime. Right, x1 prime, y1 prime, y2 prime, x1 prime and x2 prime. Now obviously, x1 is different than x1 prime. X1 is different than x1 prime, y1 is different than y1 prime, and the same is x2 is different than x2 prime, and y2 different than y2 prime. But what about the distance between them? And what is the distance? The distance is x2 minus x1 squared plus y2 minus y1 squared. Right, this is d squared. Right, and this is of course equal to d prime squared, which is x2 prime minus x1 prime squared plus y2 prime minus y1 prime squared. All right, so what we say in Euclidean space is that the distance is invariant under coordinate transformation. Right? In simple Euclidean space. This is a two-dimensional example. So the interval really plays the same role as the distance. Analogy, right, in four-dimensional space-time. Okay? Each point separately has different coordinates as seen from different observers. But the distance is invariant. Okay, is that analogy clear? Does that make things clearer in your head? No? Okay. Now we're in a position to start discussing Lorentz transformation. Now this interval that we have here, this is what connects the space and the time into one entity, which is known as space-time. Okay? Invariance of this interval quantity. By the way, questions? Look a little bit unhappy, and this is too early stage of the course to be unhappy. So how do we call this space? I'm sure you know. This is Minkowski space, very good. So we have a 4-dimensional space-time. This is known as Minkowski space. I'll write his name properly, yes. Now, in this space, as I already said, we describe events. Okay? Now, we describe an event by 4 quantities. 3 space quantities and 1 time. Okay? Now, again, I'll stress it again because it's going to save you a huge amount of trouble if you think of things in terms of events, not in terms of other things. Right? Think of events. When we speak of interval, we speak of interval between 2 events. Okay? An event is something, the simplest there is, right? Something specific had happened. 2 particles interact. This is an event. A photon was emitted. A photon was absorbed. This is an event. Okay? It is specified by its space coordinate and time coordinate. Okay? You all with me? So, to specify an event in Minkowski space, in this space, we speak of events. Okay? Each event is specified by its time and location, spatial location. So t, x, y, and z. Now I'm going to slightly change the notation. Okay? It's a little bit going to be slightly more confusing at first, but you'll get used to it very quickly. I'm going to write down, rather than t, x, y, z, I'm going to use coordinates, which I'll put them as 4 vector coordinates. I'm going to call it x mu. Now it's very, very, very important that when you copy, the mu is an upper index, it's not a lower one. Don't write that. No, x mu with an upper index, such that x0 is c times t, x1 is what we call x, x2 is y, and x3 is z. Yes?
When you show the mathematical justification for why it's upper, you see something lower, or we just
I will right now just accept it. We will thoroughly discuss that. Right now, simply accept what I'm saying. Okay? This is a definition. X mu, right? This is, let's call it 4 vector of coordinates, or coordinate 4 vector. In very, very, very old textbooks, you'd find x4 rather than x0 here. But they're so old that I don't even bother referring to that any more than that. Now, again, as a convention, if we need only the space components, only the spatial components, then I will refer to the index as a Latin index rather than a Greek index, right? I'm using a Greek letter here, mu, right? When referring to only the space components, I'm going to use the Latin indices. So so when referring, how do you say? Referring, I wrote it right, referring to the space component only, we will use Latin indices. Latin indices. So xi, right? That means that x1 is x, x2 is y, and x3 is z. We will get to that when we speak about cosmology in the last part of the course. Okay? Now it's a little bit more confusing, but it does not contain any further information, right? Just the t, x, y, z. Now before I'm going to proceed, before we can proceed, I'm going to introduce to you another matrix, 4x4 matrix, which has a name. It's called the metric matrix. It's a very simple matrix. It's a 4x4, but it's quite a simple one. Let's leave it here for now. So let's introduce 4x4 matrix, which is so important it has a name. It's called a metric, known as the metric. And for that matrix, we're going to use lower indices. So I'm going to call it with eta, mu, nu, 2 indices. And it's a very simple matrix. It's just -1, +1, +1, +1. Everything else is 0. It's a very simple matrix. On the diagonal, you have a -1, and then a +1, +1, +1, and everything else on that matrix is 0. I just call it a metric for now. Okay. Just call it a metric. And the importance is that you don't forget that the indices I put are lower. Don't write indices which are upper here. Okay? Now I should, put a star. In some fields of physics, especially quantum field theory, it is also making use of this matrix metric, but then it's defined for some reason with an opposite sign. So in QFT, for example, and possibly in other branches of physics, eta mu nu QFT is defined as a +1 minus, -1, -1, -1, and everything else is 0. I tried very hard to understand why this notation has been kind of became popular. The main reason I see is to make communication between people that do astrophysics and GR and people that do quantum fields more difficult. Physically, there is no meaning. It's completely meaningless, right? Just that you know, have it in the back of your mind. I'm not sure how it is in condensed matter. I think in condensed matter there is also some use of this matrix, and I'm not sure if this is defined with a plus or minus signs. Okay. So using this new notation that I just introduced, we can write down the interval, right? The same interval I wrote down here in a much more compact form. Delta S squared, right? It's written here, minus c delta t squared plus delta x. Right? This is just summation, right? Sum over mu and nu of eta mu nu, and then delta x mu, delta x nu. Now, this is identical to what is written here. Is identical. Do you see that? Mu and nu, of course, goes from 0 to 3. 0, 1, 2, 3. So if mu and nu equal to 0, eta 0, 0 is a minus 1. Delta x 0, delta x 0. We just c delta t. So I have a minus 1, c delta t squared. If it's equal, mu and nu are equal to 1 and 1, then I have a plus 1. Then delta x 1, delta x squared. If mu is different than nu, then the matrix gives me 0. Yeah, is that clear? So, just to further confuse you, I'm going to remove this summation. This is called Einstein summation convention. Every time we see an index that appears once as an upper index and once as a lower index, it is understood that we are summing over this index. This is known as a dummy index. So I can simply write this eta mu nu, delta x mu, delta x nu. Okay? This is known as Einstein summation convention. If you get confused, every time you see an equation in which on the same side you see an index that appears once as an upper index and once as a lower index, it is understood that you're summing over this index. Okay? So this is known as Einstein summation convention. Again, this and this are the same equations, simply written in a more compact form. Questions? No? Okay. So now we are in a position to describe a Lorentz transformation. So what is a Lorentz transformation? Any clue? What's that? A Lorentz transformation is a what? What is a Lorentz transformation? Okay, so this is a transformation from one coordinate frame to another coordinate frame, right? Is a transformation from one coordinate frame one coordinate system to another. That what? Any transformation will do? exactly. Very good. That conserves the interval. This is a definition of a Lorentz transformation. Okay. Now we can think of several such transformations, right? So one basic example is a translation. So translation means that x mu goes to x mu prime, which is just x mu plus a mu. I just added a constant to one of the coordinates. Right? A mu set of 4 fixed numbers. I just changed the origin. Now note there is a subtlety of notation here, right? I didn't say x prime mu, I say x mu prime. Right? Because x, if mu is equal to 2, right, this is x2. Right? So if mu is equal to 2, right, then we have, right, x2 prime is just y prime. That's why I use the prime on the mu. Obviously, when I make a translation, then the difference, delta x mu, is unchanged. So the interval is unchanged. Right? The only other kind of a linear transformation is to multiply this 4 vector by a linear matrix. This is the only other thing we can do. Right? See? The only other option we have is to multiply the 4 vector x mu by a matrix. So I'm going to write down x mu prime is equal to lambda. Okay, pay attention again. Mu prime, now there is a space here, and then nu. X nu. Okay. One upper index, one lower index. They are not one on top of each other. It's like there is a space here and a space here. The space here is occupied by mu prime. Upper index, the space here is occupied by nu. Lower index. Right? Lambda mu prime nu is not the same as lambda mu prime nu. Lambda mu prime nu doesn't exist. This stage, I just ask you to follow my notations very, very carefully. The later stage, you'll understand exactly what I'm doing here. I'm not going to leave you out in the darkness. Remember, I'm using Einstein's summation convention here. So really, what's written here? I need to add a summation on what is the index? Nu, right? So what is really written here is x mu prime is equal to lambda mu prime 0 x 0 plus lambda mu prime 1 x 1 plus lambda mu prime 2 x 2 plus lambda mu prime 3 x 3. That is what written here. I can also write it as x prime equal lambda x, but I'm not going to use that, so let's not even write it down. Okay? Yeah?
You said previously that the other option is to multiply by linear matrix. What is the matrix?
This is the matrix. That's
You
it.
said the word linear.
Yeah.
So what is linear?
I'll answer that in a second, okay? Wait, this is a matrix. I said I'm going to multiply it by a 4 by 4 matrix, right? But this is a general matrix. This is just a general one, right? What did we say about this Lorentz transformation? It needs to conserve the interval, right? So what does it mean, conserving the interval? So what are the requirements on that matrix? What?
Should be unitary.
Wait with that, okay? Let's go with the conservation of the interval.
That implies that
Yeah, just, so what is the interval, right? Delta S prime, right, in squared. What is it equal to? Yeah, right. If I'm using this one here, right, it's eta mu prime, nu prime, delta x mu prime, delta x nu prime. This is the interval as seen in the frame of the primed observer, right? Now this is equal to eta mu prime nu prime. Now delta x mu prime is equal to lambda mu prime, let's call it rho, right? Delta x rho. And then delta x nu prime is just lambda nu prime sigma delta x sigma. Right? I'm just using the definition. We'll see about this unitarity and linearity in a second. Okay? Now, we want that to be equal to, so we demand that this is equal to delta S, right, to the interval, and the interval, well, is just eta rho sigma delta x rho delta x sigma. Just delta S. Okay, careful attention. Rho and sigma, and here also mu and nu, or mu prime and nu prime, are just dummy indices. I could write a different, alpha and beta, it doesn't matter. I'm summing over them. Okay? Since when I write it like that, that means that I'm doing the calculations term by term. So I can switch orders. There's no problem with switching orders when I do it like that. Okay? So overall, here we get what are the conditions for conservation of interval. We want to have, since we have delta x rho and delta x sigma, then what we want to have is that eta rho sigma is equal to lambda mu prime rho lambda nu prime sigma And then eta mu prime, nu prime. Yes.
Again, why can you switch between multiplication?
Because I'm doing it term by term. When I do multiplication, when I write it like that, I refer to the terms inside this matrix one by one. Lambda 0, 1, x 1. Okay? If I were to avoid that, I would just write x prime is equal lambda x. I couldn't do it because here I'm multiplying a matrix with a vector. But when I multiply term by term, I can switch the order of the terms. So this is any matrix lambda that fulfills this equation is a legitimate Lorentz transformation. Now I think that the word linear that I used was not in place. Unitary is in place, but now you can see exactly what it means. Any matrix that fulfills this equation is a Lorentz transformation. The set of all transformations, they form a group. In group theory, it's called a Lorentz group. There is a close analogy to the rotation group, the O3, that we have. It's, of course, in 4 dimensions, so it's slightly more complicated. But in fact, it's not very much more complicated. It's pretty much the same. So let's give 2 examples, which basically cover the entire set that we're interested in. So the first category of the Lorentz transformations that we have are simple rotations. So, example 2, rotations. Right, for example, a rotation in the xy plane around the z-axis, I'd write down as lambda mu prime nu is just 1 in the time. Then we'll have a cosine theta, sine theta, minus sine theta, cosine theta, 0, 0, 0, 0, 1. Right? And if you get confused already, remember this is time x, y, z. This is a simple rotation around the z-axis. Now I argue that this rotation is a completely legitimate Lorentz transformation because it fills in the criteria that we just set for Lorentz transformation. Now this is very straightforward to show by simple direct summation. Yeah.
Shouldn't you wrote that example without the indices?
Oh no, where's the indices? These are the indices. I'll show you. For example, right?
Because previously you wrote x prime equals to lambda x as a general.
Ah, okay. It should be x t prime y. Okay.
No, I mean the lambda itself.
No. It's important that you see. I mean, I could write it like that, but it will make it more vague, I think. No, I think it's less consistent. Let's show that. Okay, so for example, we said that we need to pick up. By the way, how many equations do you see here written on the board? If we go term by term. Why 8? 16 equations, right? rho and sigma, each one gets a 4 components. And each equation, how many terms does it have on the right-hand side? 4. Right? So for example, eta, for example, let's choose rho and sigma equal 1. Right? So what's written here? Eta 1, 1. What is eta 1, 1? 1, 1. That's right. Remember the matrix eta. Right, is equal to what? Lambda mu prime 1, lambda nu prime 1, eta mu prime nu prime. Right? I just copied, I just put rho and sigma equal to 1 in that equation over there. Now remember eta, right, mu nu, was just minus 1 plus 1 plus 1 plus 1. What?
Eta 1, 1 would be negative 1.
Did I miss something?
At the left of
Eta 1, 1.
is equal to minus 1.
Why minus 1? It takes time to adjust. Okay? So, lambda mu prime 1 right? Lambda nu prime 1 eta mu prime. Now, mu prime has to be equal to nu prime, right? Otherwise it will get 0 from here, right? If it's 1 and 2, it's always 0. So it has to be the same. So we have lambda 1, 1, lambda 1, 1, eta 1, 1. Plus lambda 2, 1, lambda 2, 1, eta 2, 2. All other terms are 0, right? Because eta will just give them zeros. So what is that? Lambda 1, 1, lambda 1, 1. What? Cosine squared theta. What is lambda 2, 1, lambda 2, 1? Sine squared theta, which is indeed equal to 1, as promised. Do you want to do another example with this matrix? Or you got the idea? Trust me? You'll do it at home. Okay? I really do it. Spend the time doing it so you'll see. I know this is new for you. And I know this is very confusing and it's going to get much worse, trust me. So if you really want to see it, do it. Spend the time until you feel you feel comfortable with it. Okay? So this rotation, you may not have thought of it. We basically, if you want to really prove that this is a Lorentz transformation, we need to solve. So we solve here one equation. We saw this is true. How many equations do we need to solve total? 16 equations, right? For all the other terms, right? So plus eta 0, 1, eta 1, 3, whatever, all the other terms, right? Total 16 equations. You have to show these 16 equations, they're all fulfilled. Okay, so this is simple rotation around the z-axis. Right? Now, of course, we can do rotations around any axis that we want. We can multiply rotations. It's not really interesting. Right? The interesting is to do rotation, but around the time axis. You know? Here we have a slight, the same rotation, but because we have a minus sign, then we need to be a bit careful, and these rotations have a name. They're called boosts. So example 3, boosts. That's the name. Which is really rotation around when the time is one of the axes that is being rotated. So rotation in the tx coordinates is denoted by d tau. And yes, you're right. You're very right. So according to our definition of the interval, using our definition of the interval, which is already erased. Let's go up again. Excuse me. So remember we had the delta s squared. Well, it is just minus c delta t. That was delta r squared. But delta r is equal to 0. Because we said delta x is equal to delta y is equal to delta z is equal to 0. So I can write down delta tau squared is minus delta s squared divided by c squared. But remember from what we wrote above, right? Minus 1 over c squared eta mu nu delta x mu delta x nu. Right? I wrote the interval in this compact form. Now we have a second observer, right? O prime. So O prime, let's say it's you guys, you're seeing me moving, right? I'm moving. Because I'm moving, the clock is not moving relative to me. I'm looking at the clock and it's not moving. I can still read it, right? But you see me moving, right? So according to you, right? You're seeing the clock moving at, let's say, at some velocity v. Prime sees the clock moves at v. So the peaks are separated by time interval delta t prime, but also space interval. Right, delta x prime and just v delta t prime. We want to be precise. So the proper time, delta tau prime, is just delta t prime squared minus delta x prime squared over c squared power 1/2. Which is just 1 minus beta squared 1/2 delta t prime. right? But if I'm in an inertial frame and you're in an inertial frame, right? According to the principle of special relativity, right? The time intervals must be the same, right? Therefore, the proper times must be the same. Right? So we must have that delta tau is equal to delta tau prime. Those observers are in inertial frames.
Question.
Yes?
You define the principle with the sentence laws of nature. Here you're using an interval.
Sorry? The laws?
You defined in the beginning
Yeah.
that this principle
Yeah.
with the laws of nature.
Are invariant, yes.
Yeah, but the interval is representing the laws of
Yes, it represents the constancy of this. It is essentially, yeah, it represents the constancy of the speed of light for the different observers. Now, since these two have to be the same, right? These two. That means that you would see delta in your frame, delta t prime, is equal to 1 minus beta squared minus 1/2 delta t. Or gamma times dt. Right? This is always greater than unity. Right? So you will see me slowing down my clock just because I'm moving. Questions? I'm not sure I'm so happy with the looks on your faces right now, I have to say. You look, I'm not sure how to say that. I keep on saying, it's not as hard as you think it is. I don't know what you think, really. It takes the time to adjust to this new notation, to this new way of writing, and possibly way of thinking. But you see that essentially, this notation that I'm teaching you, this language, gives you identical results to the results that you got in first year. It is, of course, much more general. You can see the full picture. You can see where it comes from. You can see that it forms a group and everything. Right? And you see the physical principle, and everything else pretty much follows directly from the math. You cannot really do anything else. More questions? Okay. The next subject is vectors and tensors. Okay, I won't really have time to discuss them now, but let me first ask you, what is a vector? What?
an element in vector space.
That's true. That's true. And what makes this? Okay, let's be a little bit less abstract. This is possibly an algebraic. This is correct. It's correct, but it didn't really say much because we need to say what is a vector space here. Really, is any quantity quantifies as a vector?
Any quantity has a direction with magnitude.
Yeah, I thought you'd say that, or at least one of you. That is true in Euclidean space, but space is not Euclidean. Do you happen to know what is the true definition of a vector? I guess not, because why would you know? Okay. First of all, we're not dealing with Euclidean spaces, right? We're dealing with Minkowski space. So obviously, a vector is going to have 4 components. Right? Now I'm going to give you the correct definition. The correct definition of a vector is any entity whose components transform in the same way as the coordinates when we are making a transformation from one coordinate to the other, namely a Lorentz transformation. I emphasize the word components because what happens to the vector itself when we are transforming from one coordinate to the other? What?
Remain the same?
It's exactly the same. Right? The vector as an abstract entity in space doesn't care about the coordinates. That's why we're using vectors in the first place, to describe physics. Right? The components of the vector change, but not the vector. Okay? And exactly how it transforms, that is going to tell us a whole lot of things. Right? So right now I just said it. This is the correct statement. This is a contravariant vector. Is any quantity whose components transform in the same way as the coordinates when we make a Lorentz transformation. Okay? I won't go further right now, but we'll discuss that. This will be the subject of next week's lecture. So right now we're going on a Purim holiday. I wish you all a happy holiday. I'm not sure what's going to happen now, but it will be a holiday. And we should resume back on Thursday. I'm still going to have a lecture on Thursday, then we'll start the tutorials after that. Now, as you're seeing, I strongly urge you, if you haven't done so far, to go and review your knowledge in special theory of relativity. You're seeing we are doing special relativity. We're just doing it in a different language, because what the aim is to teach you the language. You see that, because we're going to use this language later on in this entire course. Okay? But so that you don't really get confused by all these math, to see that this really is corresponding. I just gave you 2 examples. This really corresponds to exactly the same special relativity that you learned in the first year. If you haven't learned, then I told you can go online to my old webpage. It is all there. Then you can go and read it. It will take you a few minutes. And then I also put my lecture notes online on the course module. You can go and look at them. Read them, and if you have any questions, then be prepared for the next lecture. All right. Are there any further questions? Are there any questions that were asked that I did not answer properly that you want to ask again? Yes. Yes.
The lecture on Thursday,
Mm-hmm.
and we discussed it, and we agreed that we could do it. We could start at 2 p.m. instead of 12.
Okay. Did you check with the secretary?
Yes.
And is this lecture hall available?
Like we didn't discuss the concrete. I wanted to ask you.
Okay. So as far as I am concerned, Thursday at 2 p.m. is okay with me. I don't have any problem. Mm-hmm. But it needs to get agreement of all the students registered to this course that they have no other conflicts.
Yes, so that's why I'm asking.
So it's good.
Everybody. So hope it's fine.
I have another course too.
There is a conflict.
On Thursday.
Before, I don't know, say 11.
What we can do, I can make a table, or you can make a table actually, of, just a small table, like, Sunday, Monday, Tuesday, and then like, I don't know, 9, 10, 11, 12, let's skip 9 because it might be too early, 12 till, I don't know, till 6, till 5, and check out everybody that is not available can just put an X, and then we'll see where we don't have X's, and then we can try to reschedule that slot there.
So I guess I can send an email and like some poll or like Google.
I leave it up to you. Okay, let's do it on Thursday. So let's meet next Thursday after the holiday, the same time, regular time, and then we can decide for the following week's Again, I'm willing to be flexible. I have some other lectures, so I'm not flexible the entire week, but I'm willing to be flexible.
Are there days when you just cannot?
I am teaching on Monday afternoon and Wednesday morning. Now we have a lecture on Wednesday anyway, so we won't have another lecture on Wednesday. Yeah, but Monday, yeah, that's my teaching, except from this course. So Sunday, Tuesday, or Thursday today in a different hour, this is good for me personally. But then I have to get the full agreement of the entire class before we switch. It's fine. Or what you can do, you can ask the secretary. I guess it's. Okay, I'm flexible personally, but again, assuming everybody agrees. Okay. Any further questions? No? Again, don't go just on holiday. Use the time now. We're just getting into things. Refresh your memory. Make sure everything is clear in your minds. We don't want to get things which are not clear. You'll see that it needs to be very, very clear in your mind, and it will be easy. Otherwise, it could be quite difficult. We don't want to get there. All right? Good. So see you. Have a nice holiday, and see you next week.